In this lesson, we'll be focusing on our innate immune system. So this lesson is called Host Defense 1. So as far as our immune system is broadly divided into two different parts, which can be further divided into three different defenses. So the two different parts of our immunity are the innate immune system and then the adaptive or the acquired immune system. So innate immunity is nonspecific, meaning it is going to act the same regardless of what type of infectious pathogen you have acquired. So whether it be virus or bacteria or fungi, we all have inherent innate immune responses that are going to act the same regardless of microbial agent. Whereas with adaptive immunity, it's much different. It's a highly specific reaction where we have specific T cells and B cells, which are called lymphocytes, which are going to respond to different viral pathogens, bacterial pathogens, and fungal pathogens, things like that. And with innate immunity, we're all born with kind of our kind of standard generic innate immune system. So we have the ability to induce things like a fever and an inflammation. Whereas with adaptive or acquired immunity, it's something that you build on after exposures, or maybe due to exposure through some type of vaccine. But it's something that you build over time. So at this point in your lives, while we may all have the same kind of innate immunity, our adaptive immunity is going to look quite different, because as we've become exposed to various things, different T cells and different T cells and different B cells have been activated to respond to those pathogens, and from that we've gotten different protective immune responses in the form of things like antibodies and memory cells like memory T cells and B cells. So it is a response that we build on over time. In this lesson, we're going to be specifically focusing on the innate immunity. The innate immunity basically can be divided into what we call the first and second line of defenses. The first line of defense are things that are going to block pathogens from getting deeper into our body. So the first line is essentially meant to block at the site of the portal of entry and prevent things from getting deeper into the body. So our skin is a huge first line of defense that blocks pathogens from getting into things like tissues. We have mucous membranes, and we even have various different chemicals that's secreted from our body, things like lysozyme, gastric juices, that type of stuff that prevent more of an internal infection. Obviously, some things are able to get past the first line of defense. For example, if you have a cut in your skin, it's very easy for a bacterial pathogen to get into the skin tissue via that cut as a portal of entry. And that's when the second line of defense would have to kick in. And the second line of defense are kind of various different internal systems that are going to protect you from infection. So this is things like inflammation, fever, phagocytosis, even different antimicrobial proteins, things like complement and interferon that we're going to talk about. And a lot of times that will stop the progression of the infection, that second line of defense. But if the infection persists, then the third line of immunity is going to kick in. And the third line of immunity is that adaptive immunity that we'll talk about later on. And that is going to be things like T cells and B cells that get activated in the production of antibodies that can neutralize the pathogen, and then ultimately memory cells that are going to protect you from any type of future exposure to the same pathogen. So in this lesson, we are focusing only on the innate immune system, so we're going to be talking about the first and second line of defenses. So first we'll talk about a few of the physical first line of defenses, the primary one being the skin. So the skin is made up of a continuous layer of cells. In micro, the most important layer of the skin is the outermost layer. The outermost layer is composed of dead skin cells, which are impregnated with a protein called keratin. Keratin is very important in micro because it's is what makes the skin tough and durable and resistant to damage by most microorganisms. So as long as your skin is intact, it is very difficult for microorganisms to get through the intact skin and into tissues. So in most cases, if a microorganism lands on your skin, it is not going to be able to get through the skin to cause an internal infection. Now obviously, if there's some type of break in the skin because of a cut or a burn, then the microorganism can gain access to the skin tissue and cause an infection. But in most instances, that keratinized layer does protect us from infection. Are there flesh-eating microorganisms? Yes, and we'll talk about those later on when we get to skin infections. But they are definitely more of the exception than the rule. Most microorganisms are not able to get through intact skin. But again, the skin has to be intact. If there is a break in the skin, even something non-pathogenic, even like normal biota, if they get into a skin wound, they could potentially cause infections. So things like Staphylococcus and Streptococcus, and even different types of fungi like Candida on the skin, while they're always on the skin and are generally non-pathogenic, if they get in a skin wound and get into the tissue where they're not supposed to be, they're supposed to be on the skin, not in the skin, but if they get into a skin tissue, they could potentially cause an infection. So skin can only serve its true function as being a physical barrier if it's kept intact. When we have some type of break in the skin, it's extremely important that we keep it clean and we keep it covered, because even normal biota on the skin, if they get into a skin wound, could potentially be problematic. They wouldn't likely cause a severe infection, but they could cause mild irritation. So another area where we have a lot of physical first line defenses is the respiratory system. Obviously, we have to breathe, and we don't get to control what we breathe in the air. There are a lot of microbes in the air, different types of fungi, viruses, and bacteria, and we do breathe them in consistently. Quite a few of them are non-pathogenic and aren't going to cause any harm, but for those that potentially could, we do have to have first line of defenses that prevent things from getting deeper within the respiratory system where they could establish an infection. So one major first line of defense that we have in the respiratory system are nasal hairs. Nasal hairs in the nose, when you breathe in, they can trap larger pathogens, things like bacteria and fungi. And usually when things get trapped in the nasal hairs, it causes irritation, which is going to initiate a sneeze. And then you're going to expel the pathogens out of your body. So they're no longer part of you. Obviously, they can be transmitted to someone else, which can be problematic, but they're out of your system in that case. And this is really good for the larger things like bacteria and fungi. Viruses, unfortunately, are very small, and they're able to very easily get through the maze of nasal hairs and establish themselves deeper in the respiratory system. But the nasal hairs can protect us from larger pathogens getting deeper into our respiratory system. We do constantly have the flow of mucus throughout the respiratory system. Mucus has a very kind of thick consistency, which a lot of times can trap microorganisms until the phagocytic cells can catch up to them and engulf them. And then there also is our antimicrobial agents or chemicals that can kill bacteria in the mucus. And then obviously, typically with mucus and things, we feel the need to cough it up, which can expel microorganisms out of the respiratory system, or even swallow it down into the stomach where the stomach acid would destroy the microorganisms. We do have ciliated epithelium throughout the respiratory system. So the cilia in the respiratory system create kind of like an upward escalator. And what that does is it prevents potential pathogens from getting lower into the respiratory system, predominantly in the lungs. We really want to protect our lungs at all costs. You do not want any type of microorganisms getting into the lungs, because if anything foreign gets into the lungs, it can induce inflammation, which can cause fluid to build up, which can lead to pneumonia. So we need to prevent anything from getting into the lungs. So what our respiratory system has done is it's put this ciliated epithelium in the upper respiratory system, and what that kind of does is create this escalator to keep things moving upward. So if an infectious pathogen is in that region, the cilia will move it upward so that it can't get into the lungs, and it's going to move it upward until it gets to the throat or the pharynx. Once it's in the throat, you kind of have two options. You can either cough it out and expel it out of your body, or you would swallow it down into the gastrointestinal system, where it would get broken down by stomach acid. But the whole goal of the cilia is to keep things moving upward to prevent infectious microbes from getting into the lungs. So our body has designed a way to get them to the throat, where we can either get them out of our body or into the stomach. We have other physical first-line defenses, which just didn't fit into the skin or respiratory specifically, but if you would get something potentially foreign into your eye, mechanically you would induce blinking, would push the microorganism out, but also there would be a production of tears, which would flush the microorganism out too. Within our gastrointestinal tract, we have the constant flow of saliva. There are antimicrobial factors in the saliva that we'll talk about in a second that can kill bacteria, but naturally that kind of constant flow of saliva to the gastrointestinal system, to the stomach, keeps everything kind of moving downward. And the stomach is kind of like the dumping grounds for anything our body needs to kill as far as infectious microbes. Our body tries to get infectious microbes to the stomach because the stomach has a very low pH due to the gastric juices, and most microorganisms prefer a nice neutral pH. So if our body can flush things into the stomach, usually the stomach acid will do the rest and get rid of the microorganisms. So that constant flow of saliva kind of keeps microorganisms moving in that downward direction to the stomach. And then just the general release of bodily fluids. I mean, bodily fluids are going to flush microorganisms out of the body. And that's why it's so incredibly important that when you're handling bodily fluids, you have to be really, really cautious, because keep in mind, bodily fluids are portals of exit. So they're going to flush pathogens out of someone's body, and we don't want any type of microorganisms in those bodily fluids to gain access into any of our portals of entry where they could potentially establish infection. So you have to be incredibly cautious with how you handle all bodily fluids. We also have normal biota, especially on our skin and throughout our gastrointestinal system and our upper respiratory system, that engage in microbial antagonism. We've talked about this in a previous lesson, but this is how those good beneficial microorganisms protect us from potentially dangerous microorganisms. So this is essentially how the good fights the bad. We talked about the different ways that this can happen before, but again, one way that it can happen is all the good microorganisms can be taking up the attachment points. So if a bad microorganism gets in, it will not have anywhere to attach. If it doesn't have anywhere to attach, then our body will eventually flush it out, whether it's through coughing or sneezing or peristalsis and moving things through the gastrointestinal system. If it can't attach to a receptor, our body will flush it out. Another thing is limited access to nutrients. You have billions of normal biota. If the normal biota have cultivated that region and they're using up all the nutrients, then there's none left over for pathogens, and they essentially starve to death. And then the last is creating that unfavorable environment so the bad pathogens cannot survive in that area. So for example, on our skin, Staphylococcus epidermidis, which is a normal biota, it feeds off of our skin oils and releases acids that gives our skin an overall acidic pH. So that way, if a bad bacteria lands on our skin, it typically is not going to be able to grow very well because of the acidic pH. But that's microbial antagonism. Staphylococcus epidermidis is a good bacteria. It created that acidic environment on the skin, so now the bad bacteria, for example, something like E. coli, would not be able to grow in that type of an environment.